Hello everyone. In today's lecture we will talk about the linear quadratic regulator. Linear quadratic regulator essentially is an optimal control method. Okay, linear quadratic quadratic regulator. This is an optimal control method. We have seen essentially optimization. So we had an introduction to optimization, where we had an objective function, which was a function of a number of parameters, right? x1 to xn, and we wanted to minimize or maximize this function with respect to these parameters. Now, in contrast, when we have an optimal control problem, we again have an objective function, but this time the objective function is not a function of a number of variables, but is a function of another function. Okay. So again, we want to minimize or maximize that with respect to a function. So we want to, in the case of optimization, we want to find the alpha values that would minimize or maximize j. And in the case of an optimal control problem, we are trying to find the control or the input u, which will minimize a function of that input. Okay, when you have a function that is a function of a function, we call this a functional. Okay, so if this is a function of alpha, in the second case we have a functional of u. Okay, and trying to solve this problem is called an optimal control problem. Okay, in our department we have courses that address these two topics. EE 553, which is a course in the control theory area. Also, a follow-up course is called EE 554, is the optimal control theory course. Okay, so the linear quadratic regulator is a special case of an optimal control problem. Okay, now let us take a look at how control problems can be formulated. Okay, so if we take a look at control problems, so the question is, why do we call this a regulator rather than a controller? Okay, so in control problems, we can have regulator problems. Okay, and we can also have servo problems. Okay. Now, what are the differences between those? Let's take a look at that. Okay. Now, in the case of regulator problems, what we are effectively saying is that we are trying to manipulate system input to counteract the effect of disturbances or initial conditions. Okay, so manipulate system input to counteract the effect of disturbances or initial conditions. Okay. Whereas in servo problems, also these are sometimes known as tracking problems. Okay. effectively what you're trying to do is to follow an input. Okay, so in this case we have to manipulate the system input to keep the system output, close to a given input trajectory, close to an input trajectory. Okay. Okay. So if we consider our general feedback system, right? We have a reference input R, and then we have a controller. Then we can have a disturbance. This disturbance can be either before the plant or after the plant, or it can be a disturbance to the plant. So we have our plant here and our output feedback. Okay. So what we are saying is in the regulator problem, we assume basically that the reference is either constant or zero, and we have a signal at the disturbance. So we want to eliminate that disturbance. Or in the servo problem, omega is constant or zero, and the input, the reference input, has a particular trajectory. Okay. So in both of these cases, okay, for the regulator problem, we have R constant or zero, and omega is variable input. And for the case of a servo problem, we have R variable input and omega constant or zero. So we will focus on the first one of these problems. That's what why we call it the linear quadratic regulator. Okay, so for now we will focus on one, which is the regulator problem. All right. Now, so what is our aim? What we will look at is that we will concentrate on the initial condition. Okay, so our aim will be to cancel the effect of the initial condition. The effect of the initial condition x0, and we will consider a state space representation for our problem. Okay, so what we will have is that we will have a system where we have x dot equals ax plus bu, and also y is equal to cx plus du. We will consider d to be equal to 0 for our purposes. X0, x at time 0 is equal to x0 is our initial condition. Okay, and we will consider a state feedback problem. So we will try to find a function of the states that will basically give us the input, and we want this input u to be such that it will eliminate or suppress the effect of the initial condition as fast as possible. Okay, so we have derived as our aim, drive the state, which is the initial state, to 0 as soon as possible. Okay. So in this problem, obviously, we have our state vector, which is in Rn. The input and the output, we assume them to be scalars without loss of generality. That means nothing we will do will be specific to u and y will be being scalars, so we can generalize everything that we do. That's why we call without loss of generality. And we have obviously the matrices as A being an n by n matrix because of our dimensions, B being equal to or not being an element of r to the n by 1, meaning an n by 1 vector, C being part of r to the power 1 by n, and okay, D will be an element of R. We will see whether we will assume that to be 0 or not. Okay, but for now, let it stay there as a scalar as well. Okay, so these 1 by 1 scalar value. Okay, so now let's come to our objective function. Okay, how do we define our objective function? To find what f of x is. Okay, so objective function is to find the optimal f of x equals u. Okay, so u will be a function that will be a state feedback. Okay, a state feedback, an optimal state feedback. Okay, from pole placement, we know that, for example, the state feedback can be linear in the sense that it can be a linear combination of all the states. Okay, so how do we define our objective function? Okay, so let's take a look at our objective function. So the objective function will be a function of u, and because it's going to also have to be a function of x. Okay, it's going to be defined as an integral from 0 to infinity, and I'm going to explain what these terms are. Okay, but it's going to be x transpose, x being a vector, t q xt. Q is a matrix that I will in a minute define, plus u transpose of t r ut. Okay, here obviously we have defined our u to be a scalar in our special case, but in general u can be a vector. Therefore R is also a matrix. Okay, dt. And J is a functional, right, as we defined before, functional. So it's a function of a function. Okay, so we have Q being an element of R n by n, n being the number of states, and R being an element of R to the power m by m, m being the number of inputs. Okay, so we have defined it as to be a scalar. In this case, R also will be a scalar, and these are known as weighting matrices. Okay, so Q and R are actually, we will define them as design variables that will determine what's going to be the weight of the state versus the weight of the input in the objective function. Okay. So the way we defined it, J is a quadratic function. Okay, J is a quadratic function. Why? Because we have square, quadratic function. It's a second order in terms of x and u. Okay. U of t is the independent function. Here, and x is a dependent function. Okay, is a dependent function because it needs to satisfy the state equations. Okay, it needs to, so we are free to select u as we want, but x of t has to obey the state equations, satisfy the state equations. Okay, so we want to minimize, or we want to find the function u that will minimize j of u of x. Okay, so this problem subject to x dot equals ax plus bu and y is equal to cx plus du. Okay, when we say subject to, these are known as the constraints of the problem in optimization terminology. Okay, so this problem overall is called the linear quadratic regulator problem. Linear quadratic regulator problem. Okay. Now Q and R are weighting matrices, but they have to be selected with a special property. So Q and R are selected as positive semi-definite, and I will define it in a minute, semi-definite matrices. Okay, so by definition, a positive semi-definite matrix corresponds to a scalar that is smaller than, larger than or equal to 0. Okay, so in order to determine when a matrix is positive semi-definite, you need to make sure that x transpose qx is larger than or equal to 0 for all x that is in Rn. Okay, so that is the definition of positive semi-definiteness. Okay, so it means that the first term in our objective function has to be positive or 0. Okay, by the selection of the Q matrix, independent of what the states does. Okay, similarly, we have U transpose RU has to be also larger than or equal to 0. Again, for all U that is an element of Rm. Okay, so this is what is defined by being positive semi-definite matrices. Okay. So what are the meanings of these two terms in the objective function? Okay, in the objective, or sometimes called the cost function, objective or cost function, right? Basically, what this term does is that it punishes large state values. Okay, so if you think about it, about our objective function, if the states goes to zero very fast, the area underneath this function will be much smaller. Okay, so if you consider, let's say this is time, and this is our state. Okay, and state starts at x0, so it goes to 0, and because we are taking an integral of kind of a weighted square of x, okay, so essentially what we are looking at is that a function that corresponds to roughly the area underneath this curve. Okay, so for example, this curve, if it is the x transpose qx curve as a function of time, the faster the states goes to 0, the smaller the area underneath, and therefore the smaller the first term. Okay, whereas the second term essentially punishes large input values. Okay, so you see that so that second term, if we again think about another function, that is this time u transpose ru, okay, and let's say it does something in order to drive the states to 0. Okay, the smaller this term, the smaller its contribution to the cost. So in order to minimize the cost, in fact, we are trying to use the smallest possible input to be able to drive the states to 0. Okay, so you can see that there is a compromise, because if you want to drive the states to 0 faster, you would need to use a larger input. But if you use a larger input, that means the second term will go up. And if you try to push the second term to be small, that means the states will be slower to converge to 0. Okay, so there is clearly a compromise. There is a compromise. Okay, so in fact, the interesting thing about the linear quadratic regulator is that it's a problem that is created to be able to generate control inputs while also respecting certain limits or certain constraints on the inputs. For example, if you have certain motors with certain capabilities, you cannot saturate your motors. You cannot go to the limits of the motors, because that's going to create nonlinearities, and you will not be able to generate the necessary torques. Okay, so by using a linear quadratic regulator, you can actually generate a compromising solution where you are trying to do your best in order to drive the states to 0 while also maintaining a certain cap on the input. Okay, so so let's write that down. Okay, to drive x0 to 0 fast, reducing the first term, we would use a large input u, making the second term the second term large. Okay, so you cannot just make the input infinitely large in order to make x go to 0 infinitely fast. You have to really strike a balance. The balance is determined by by the two matrices Q and R, which are now the design parameters of this problem. So those two matrices have to be selected by the user, and we will talk about at the end of this topic about how to choose properly Q and R. Okay. Now, now in the next video, we will start talking about how to solve this problem. Okay, and normally the solution to this kind of problems is the topic of the optimal control theory. There is a branch of mathematics called the variational calculus, which specifically attacks how to use calculus for functions of functions. Okay, but since we don't know about this particular branch of mathematics at this point, we will try to go through an example, and we will try to do some clever tricks in order to find a solution for our problem. Okay, so that's going to be the topic of the next video.